Hello everyone, thanks for tuning into my presentation. My name is Dolly, I'm a postdoc working at Munich University. Today I'm going to show our preliminary dynamic rupture model for the 2021 magnitude 8.2 Chignik, Alaska earthquake. This work is in collaboration with Bo Li, Thelma Utrecht, Shihao Yuan, James B. Miller, Kang Wang, and Alice Gabriel. The Aleutian Alaska subduction is a plate boundary between the Pacific plate and the North American plate. Several large earthquakes have taken place on different segments along the fault. The largest one is the 1964 magnitude 9.2 Prince William Sound event that have caused a destructive tsunami wave. The Yosemite segment hosted the event this year and the 1938 magnitude 8.3 earthquake. However, whether the rupture area of these two earthquakes are overlapped is not clear. Next to Yosemite is Shumagin Gap. The Shumagin Gap has no significant seismicity except for the two 2020 magnitude 7.8 and magnitude 7.6 events. The earthquake behavior and how it is related to the plate tectonics on the fault is not known yet. The figure on the right shows the fault locking model and the proposed segmentation by Juve and Freimüller, 2020. The yellow and red stars represent the epicenters of the 2020 magnitude 7.8 and the 2021 magnitude 8.2 event. We can see both earthquakes appeared on the weakly coupled portion on the deeper fault, with nearly no shallow slip. The 2021 Chignik earthquake stops before reaching to the adjacent firmly locked fault segment. It is not clear how that the background stress condition could drive the origin and rest of the magnitude 7.2 earthquake. This motivates us to use dynamic models to probe the mechanics of the earthquake behavior and the implications for future seismic and tsunami hazard. There is an assumption that the earthquake behavior is related to the oceanic sediment and pore fluid pressure on the fault. The figure on the right shows the seismic imaging of P-wave velocity, which gives the detailed structure of the sediment layer on the top of oceanic plate. Compared to the sediment layer on Shumagin Gap, Yosemite have a relative high pore fluid pressure and a thicker sediment layer. The normalized pore pressure ratio is up to 0.8. From lab sharing experiments, we know that pore fluid is sensitive to temperature. It will increase very fast during high slip rate due to frictional heating and consequently weaken the fault. Taking into account the thermopressurization effect could explain the enhanced shallow slip in Japan Trench in a 2D dynamic model study. Thus, the pore fluid pressure on subduction sediment layer is an important ingredient in this research. We built our numerical forward model using the discontinuity Galerkin finite element method. Our software is called SESO. It employs adaptive unstructured tetrahedral mesh and thus can approximate the complex fault geometry and topography. It has been optimized on high-performance computing and thus can achieve high-order accuracy with reasonable computational expense. We also account for the slab geometry, tectonic loading, and high-resolution topography data in our model. We also consider the lab-derived constitutive friction loss to control the fault strength. We incorporate the fault weakening by the effect of thermopressurization. The feature of thermopressurization of SESO has been validated in SCAC benchmark. The initial stress will significantly affect the nucleation, propagation, and the rest of dynamic rupture. We assign the relative initial stress on the fault constrained by the geodetic fault coupling model in semi-D and cardiac. We assume the slip deficit has been balanced by the 2020 magnitude 7.8 event in shoe margin gap, and thus the shear stress level there is very low. The figure on the right shows the stress ratio, which is defined as the ratio between a strength axis and the stress drop in semi-D and cardiac segment. We see that on the semi-D segment, there is a higher S ratio, which means that it's less closer to critical failure than a cardiac segment. Besides the relative fault strength, the absolute initial stress is determined by the effective confining stress. We assign the depth-dependent distribution of effective confining stress, assuming variable pore fluid pressure along the fault. The solid and the dashed line in Figure A represent the cross-section profiles in semi-D and the segment in Figure C. The normalized pore fluid ratio in semi-D is 0.8 in our model. For a cardiac segment, we assume hydrostatic pore fluid pressure. The friction parameter A-B in subduction fault is depth-dependent, with a shallow transition supported by frictional experiment of drilling samples in New Zealand. The deeper transition is consistent with the temperature-related brittle to viscous transition. We cite different thermopressurization parameter for the two segments on the fault. The hydraulic diffusivity and the shear zone half-width are chosen within the range of the lab experiments of fault zone material. The higher hydraulic diffusivity and the smaller shear zone half-width in the west part of semi-D segment will have a higher heat generation and larger pore fluid gradient in the simulation. Now I will show our simulation result. The snapshots shows the slip rate on the fault. We see a crack-like nucleation around the hypocenter and gradually grows into a more pulsive rupture front due to the friction weakening and the thermopressurization. The rupture front became narrower to the west and finally stopped before going into cardiac segment. The shallow fault didn't rupture because the low initial shear stress and the velocity strengthening on the fault. We compare our model result with USGS inversion. In our dynamic simulation, the largest fault slip is about 8 meters appears around the hypocenter. This is slightly higher than the maximum slip from USGS inversion. The rupture length along the fault and the rupture arrest is comparable with the inversion. We also expect a more insight from the comparison to higher resolution multi-data kinematic slip inversion result. To understand the effect of thermopressurization, we plot the fault slip rate, the pore pressure and the temperature with time at point A and B. The pressurization of pore fluid started immediately after the beginning of fault slip. At point A, pore pressure increased up to 25 MPa and then gradually reduced to a constant level. The temperature increased by 700 degrees. At point B, the fault slip is slightly lower than at point A. The change of pore pressure and temperature is 5 MPa and 50 degrees respectively. From the comparison, we see point A is more affected by the weakening of thermal pressurization because of the initial parameter setup. The map view shows both a long strike and a long dip variation in temperature and pore pressure change on the fault. The intensive weakening of fault is necessary for the rupture to initiate and propagation around the hypocenter. We observed that the rupture will not sustain if no thermal pressurization effect is included in the initial setup. We also compare our modeled GPS with the GPS data downloaded from UNAVCO. Both the direction and the amplitude of the horizontal vector are very similar to the data. However, the vertical displacement are much smaller compared with the real data. It might contribute to a two-flight subduction plate in the SLAB 2.0 model. An improved SLAB geometry might improve our comparison in our future study. The vertical displacement for the inversion and the simulation are both as small as 2 meters and no significant slip near the trench. This displacement is really small to generate a destructive tsunami wave. However, it doesn't rule out the potential of tsunami hazard since the shallow fault strength and stress conditions are not clear yet. To sum up our study, we use 3D dynamic rupture model to highlight the interplay of slab geometry, friction, and pore fluid pressure governed by a fault heterogeneity in our model. We find a thermal pressurization plays an important role in earthquake initiation, propagation, and rupture arrest. The lack of shallow slip in the earthquake might be attributed to the shallow velocity strengthening portion. We observed strong trade-offs of rupture nucleation, termination, rapid dynamic weakening, realistic heat production, and fault strength and stress initiation in our model. Unless we have more observational constraints, we cannot rule out other mechanics in the earthquake. We are still working on improved model by taking into consideration a more comprehensive and realistic model parameter setup. We are also planning to compare our result with regional seismic networks and INSAR imaging. Thanks for listening. I'm happy to take any questions in our on-live discussion part on Friday, December 17th.